Viterbi algorithm is used to find the most probable state path, so that generated the output. It's a decoding algorithm. So let's have some execution of this algorithm with an example so that you guys should understand what's going on those ugly equations. So we have those two states. For example, here in this example, we have a high GC content state. We call it as H for high, and we have a low GC content state. So maybe the first one is coming from coding regions, the other one is coming from non-coding regions. We recognize that there are two states, so our Q is equal to 2, which is high and low. We can start from anywhere, and we can start in high. The probability is 0.5, and 0.5 are half and half, so it's quite fair, and you can move into any directions. While you are in this high states, you can stay over here 50% of the time. You can move to the low state. While you are in low state, you can stay there for 60% of the time, and you can get back to state H 40% of the time. And within each state, which symbols you emit, your alphabet size is 4, A, C, G, T. You can have A 20% of the time, C and G both 30-30 in case of the high GC content. So you can see you have higher proportion of CGs 60% of the time, and again 20% you can have T. While in low, you see that your CGs are 0.4, they sum up to you can say 40%. So most of the time you observe A's and T's. So in this example, I'm putting one more thing in your equation. So VL is in addition to I, we have J in order to accommodate what position is it and what symbol is over there. So that is equal to ELXI, that is the emission probability or probability of seeing I in state L. This max K VKJ into I minus 1 is the probability or the probability of most probable path ending in state K at position I minus 1 with an element J. Don't be confused with the previous J over here. So these elements can be same or they can be different. Sorry, I should have used different symbols. And this is then multiplied with AKL. So that is the probability of transition from state K to L. We can elaborate with this example. So right now we are at position number 4 and we are looking into a symbol that is A. We can put it into this equation, which was right here. So the probability of most probable path ending in state H with observation A at 4th position, while saying it's like this, while putting into the equation, it looks like this. So where we can see that VL and then we see A at 4th position. So it's since we are expecting this to coming from this state H, so we have AEH O into A and maximum of any option. So right now we are in state H, but in the previous position it can be either coming from state L or coming from state H. If it's coming from state L, so we will take its probability coming from state L. So at position number 3, we observe there is another element called as C. So whether this C is coming from state L or coming from H, we can take those two probabilities, multiply both of them, and then this we can get the probabilities while this C was actually in state H. So that is VH into C3, and then since our this symbol present at position number 4 is in H state, so we will multiply with the probability of moving from H to H or staying in the same state. So that is the transition probability over here. So as per the algorithm, we will pick up whichever gives us maximum from either this one or this one. We can compute recursively from first to the last element the probability of most probable path. So in this way we can work for all those symbols, all those elements in this particular string. Since we are dealing with the probabilities which are really small numbers, and multiplying those small numbers with one another creates underflow errors, so you get really small numbers. So in order to avoid that, there is a technique where we can scale them in a log scale, and most frequently log 2 scale is being used. So these are natural numbers at the top, 1 by 16, On log2 scale it is -4. Actually it's when you calculate that, it's 1 by 16. Actually it is like this. So that is actually your 2 raised to power 4. So when you bring it up, it becomes -4. In same way, 1 by 8 is represented as -3, 0 as -infinity, and so on. We have number 16 is represented as 2 raised to power 4. So the log2 value for that is 4. So in this way, our small numbers become those whole numbers, and we can multiply them. But one more thing is, while you are multiplying the things in log scale, you need to sum them up. So our equation then becomes something like this. So we can take those probabilities and convert them into log2 scale. Now our whole numbers are like this. And now let's do one more activity to understand it completely. So what is the probability of this G, G, C, A, C, T, G, A, A? We are starting with G. So at position number 1, what is the probability that this G is coming from H? So we take the transition probability of starting in state H, so that is -1, plus we have already taken those logs, so we will add those values rather than multiply them. And what is the probability of this G in state H? So that is -1.737. So that is -2.737. Same way we can calculate the probability of starting in state L for this G, which is -3.322, which is most likely obviously the ones that have the higher value, since numbers are negative. So -2.7 is the higher value. So most probably it's coming from this state H. Let's move into one more nucleotide further. What is the probability of moving or observing this G at position number 2? We can calculate for this sequence to be coming from state H. With this, we can plug in the values and then we sum them up, and in the end our number is -5.474. Same way we can calculate for this position number 2 the possibility of getting a G over here from state L. So we plug in the values, we pick maximum among those these two, and our answer sums up to -6.059. So in the end, what we conclude, since we are looking for the most probable path, we are looking for the maximum values. So first possibility, that is coming from state H, is high. So we do that the same for all nucleotides, and in the end we fill in those all those options. So on the rows we have both the states, and on the columns we have our sequence. So we put all those possibilities and then we put our pointers. So in the end the cumulative probability is -24.49, which is ending up in, for the last nucleotide to be ending up in state L, and ending up in state H is -25.65. We have those pointers from where we are getting these numbers, so we can trace back, and in the end we can conclude that the most probable path is this. So it started and stayed in HHH, and then it moved into LLN, and the overall probability of this sequence is this one. So Viterbi algorithm is used to find the most probable state path, and this is the decoding algorithm. So in this example we try to understand how it works.